combinatorial interaction testing. And same as always, when you have questions, just let me know. We are in the fortunate situation that you can ask right away. Today's slides are mostly from Justina again, but I've made a couple of tweaks and extensions of these. And it's about combinatorial interaction testing. This problem has one or two big advantages. One is it's very easy to formulate it as an optimization problem, very straightforward. Another one is there are specialized algorithms for this problem. So yes, we can use some of the algorithms that we've talked about in last week's random search. What else have we talked about? Hill climbing. The family is bio-inspired or genetic algorithms.
And then there was annealing.
Simulated annealing was maybe something in the middle, correct. So we can use all of these, but there are also specialized algorithms. And this is good because sometimes you understand so much about a problem domain that you don't have to use these general purpose heuristics, these meta-heuristics they are sometimes called. Heuristics are typically algorithms that are, or approaches that are problem specific, and meta-heuristics, they're a bit more meta, a bit more abstract. They are, you can adjust them for lots of different problems, whether it's logistics, whether it's software engineering, and so on. So there's lots of information available online. This domain is nothing new, but it's important for us to just go through them and see what are different approaches now. How can this be of use later on when depending on what kind of company you'll be working in later. Now, combinatorial interaction testing is in principle nothing new. So about 300 BC, there was one famous book. Well, this is the English version, the English title of it. It's a collection of about 36,000 questions and answers. And one of the questions in this particular book was something along the following. So given you have 6 spices, how many different combinations are there of, let's say you pick one spice, or you're allowed to do any pair of spices, or a triplet of spices? Do you want to have any guesses now already? Otherwise I'll just rush now. So let's say it starts with 1. How many combinations of one spice can you have? That's maybe a bit weird, the formulation, given that you have 6 spices. How many single picks can you have, different ones?
The number of spices.
Yeah, 6, correct. How about 2? You're not considering order, so whether you take A and B or B and A doesn't matter. So A and B is one combination. So A, B, B, A is one combination. How many combinations would we have there? 12, you say? No. Let me see. So if you got 6, if you don't have all factorial ones because of the orders. Let's see. I can't remember the number right now. So you've got all 6. So picking 1 is easy. No, 6. 2. So 2 out of 6. Can you? So these have been binomial coefficients. Can you calculate this? Have you seen this a while ago? Maybe in high school math. Can you calculate? Well, the factorials, exactly. Do you remember how to do this by hand? I think one of them, I'll start it. 6 factorial divided by what? Not just the rightmost one. No, n minus 1. If I remember correctly, it's 2 factorial times 4. 4 factorial. That's the upper one times, so if it's n out of k out of n, and it's n factorial. Okay, over k factorial times n minus k factorial. So in this case, 6 factorial is, well, we can rewrite this a little bit, times 5 times 4 factorial. This cancels out. Here we've got a 2, here we've got a 3 now. So 3 times 5, I think you said 15, right? Yes, so very good. Hope that's correct, 15. And if we go to 3 out of 6, well, we could use the same formula again, but it gives us another 20. So 41 combinations. Very simple problem, a little bit real-world related. I'm not sure how often you have that particular problem that you have to pick spices from a particular collection. But in software engineering, we have similar problems quite often. We have got lots of parameters and lots of options or values for these parameters. Now, it has taken, after this one example about the spices, about 2,000 years for this idea to creep into software engineering and computer science as well. And probably one of the first resources that talks about some form of interaction testing is the one here from 1935, where somebody talked about the design of experiments. This hasn't, back then that didn't have much to do with software engineering itself, but it was very important given that now that new larger systems have come up, it was important to investigate how to test these systems, how to design experiments, given that you have so many parameters. And that idea later even made it into products. So some companies in the mid of the 20th century have actually sold what they've called decision tables. They made money with creating tables, creating combinations, creating experiments for customers, because there was no software support, unfortunately. And these were then handed out as papers or pages on paper. But nowadays, luckily, we have a lot more support for this, so automated support. Now, somewhat related, and this brings it a bit closer to mathematics and the computer science domain, is the idea of Latin squares. Latin squares have something to do with Sudoku, and essentially the idea is that you have an n by n array, could be n parameters or so, and in each diagonal or in each column, so you could see each column maybe as a parameter, each row could be maybe a test case, and the idea is that you'd have each value for each parameter somehow covered once in each column, each diagonal, and each row. Yes, row, column, diagonal. So yellow is here, but you don't have two yellows in one column or one row. And this, so that brings it a little bit closer to the proper, well-founded research. Now, interestingly, in 1985, Robert Mundell thought that once you have these Latin squares, it is actually an equivalent to exhaustive testing. And that was just wrong. So he thought about this for a while. Maybe there are some hidden assumptions that I'm not aware of right now, but it doesn't make sense. You cannot, what are all the combinations? You cannot compress everything into something of quadratic complexity, when normally the complexity is exponential. Because of all the combinatorial explosion, you've got 9 parameters. In this case here, 9 parameters with 9 settings. So in total, your space of combinations is 9 to the factorial. Nonsense, not 9 to the factorial. 9 to the power of 9, and not 9 squared, which is a lot smaller. You cannot capture everything, not all. So it's definitely not equivalent to exhaustive testing. A little bit later, once people started to investigate this a bit more, the idea of orthogonal arrays came up, and the idea with orthogonal here, you might remember that from geometry, is you have a 90-degree angle between lines or segments. And in testing, you could think of orthogonality as in trying to have as little overlap with other tests as possible. In higher dimensional spaces or with test cases or parameters, orthogonality doesn't immediately make much sense. But intuitively, when you carry it over, thinking of not redoing some of the work that you have, or some of the test cases, or some of the tests that you have run before, it should help you to minimize the resources that you spend on testing. One example here, super small one, quick one. I think that comes up now. Let's think of 3 parameters. Each one has values 1 and 2, and each row here is one test case. We've got also test case 1, test case 2, test case 3, test case 4. And essentially, whenever you look at two of the parameters, let's say, or columns even, 1 or 2, 1 or 3, 2 and 3, in each cases you always have the combination or the value combinations of 1, 1, 1, 2, 2, 1, and 2, 2. So 1, 1 here, for example, 2, 1, 1, 2, 2, 2. Here 1, 1, 2, 2, 1, 2, 2, 1, and here 1, 1, 2, 1, 2, 2, 1, 2. This means that for this particular table here, and the 3 parameters, and the 4 test cases, you're covering all pairs of combinations. Not all 3, because that would require 8 combinations, like when you do binary, also you check the binary representation. But here, if you're just after the the pairwise interaction of certain values, these 4 test cases are enough, instead of 8. And the rest of the day will mostly be about how to create such tables that are not super long, as compact as possible. It is a surprisingly difficult problem, and for academics who like to do research in that area, there are some websites out there that collect as small as possible these arrays here. Where would you have them? Are these tables? Because it's for 3 parameters and 2 values each, creating this takes virtually no time. But if we think of 20 parameters and 20 values, this it would just take an enormous amount of time. And we researchers, we like to benchmark our approaches against other existing systems. So this is why some people started to collect solutions. Some of them are provably optimal, some others you can still improve a little bit further. Now for your homework, you can look up this website, but you will not find a solution to your particular homework. So combinatorial interaction testing will be part of assignment 1, or is part of assignment 1. And another work, or say similar to orthogonal or arrays, another term is covering arrays, which is essentially the same. Or for our purposes, it's close enough.
By mistake, I started the assignment for combinational V1, but I didn't submit it, so I closed the window.
Oh, that's
so
fine.
That wouldn't count as an attempt, right?
No. For the assignment, you can submit as often as you wish to. For the quiz.
Yeah.
Okay, good. I think you have to actually submit it in order to have it as an attempt.
Yeah.
That having said, I normally don't see the student view. So if for some reason you think that it was counted incorrectly, let me know afterwards and we'll figure it out somehow. But I think you have to actually press the submit button and then it counts.
Because it was still showing number of attempts too.
Yeah, okay, then everything's fine. That's good to know, yes. Good. Super brief history of combinatorial interaction testing in software engineering. Well, about 2,000 years before that, you have had that riddle, the quiz about the spices. Yeah, the decision tables came up in 57, and lots of companies have taken over the ideas or adopted the ideas. So AT&T, for example, Chrysler, somewhere was Microsoft as well. And at times they have brought out specialized tools as well. So a lot of theory, people sat down and thought about the problem as a combinatorial optimization problem, so on a very abstract level, just thinking of parameters and values, not so much of, let's say, cars or web forms. So they've come up with lots of problem-specific approaches to this problem of creating a test suite that is as small as possible, because otherwise you have that exponential search space. In general, combinatorial interaction testing is a black box technique that takes inputs or samples inputs and configurations and parameters, and it combines them in such a way that, well, it says here systematic fashion, so that you achieve a particular goal. For example, that you investigate or that you check all pairwise interactions. To go a little bit into details, so black box testing normally means that you take the entire program just as it is, and you don't unpack it, you don't look into the source code itself. In contrast to this would be white box testing, where you have, for example here, you check coverage, statement coverage or branch coverage. So this would be testing the system, testing components, measuring something about components of the system. I'm going back briefly. So in black box testing, you're just considering the box as the entire system as a box. Values go in, some behavior, some values come out. That's all. It's good enough for us, for our purposes. Let's look at an example. let's say we want to book a flight from London, we want to go on holidays to Spain, and we're not entirely sure where we want to go, so let's say maybe Barcelona or Madrid. That's here just simply the situation, so 2 options here. And we want to go there for roughly a week, but we might leave on either the 20th of August or the 21st of August, and we return maybe on the 26th of August or 27th of August. So we have a bit of a flexibility there. We can visualize this in the table very easily. We've got, say, 1 option as a target country, 2 options for the cities, 2 options for the departure date, and 2 options for the arrival date. You can also think of this data or this table to essentially encode parameters and values. 4 parameters, and in some cases you've got 1 value, for example for the country, in other cases you've got 2. For this setting here, well, what are in total the different combinations that we might want to consider? So, said we go from Spain either to Barcelona or Madrid, either on the 20th or 21st. So we've got 1 choice for the country, times 2 choices for the cities, times 2 choices for the departure date, times 2 choices for the return date. So in total, this seems to give us 8 possible inputs. And ideally, as outputs, the software doesn't crash. So, but that's all. We are concerned about the inputs. So these are all the parameter value combinations. 4 parameters, sometimes one value, sometimes 2. In total here we have got 8 combinations. And this can now be our test suite. 8 cases for this particular holiday, short holiday. Now, if we make this a little bit more realistic and just say, here we want to go from London to, well, almost anywhere in the world on any day of the year, we end up having lots and lots more combinations. Any idea how many combinations this could be?
80 into 184 into 365 into 365.
It's 80 times. Yes. So it's a lot of combinations. So was it 10 to the 9? So millions of combinations. And this is unfortunately just simply a consequence of the combinatorial explosion problem. You've got combinations of different parameters or different values, and that's simply the consequence. We come across this here in this particular example of testing. We have this in logistics. We've got this in lots and lots of different problem domains. And it is something that we have to live with. Very often there are no simple approaches to this, and all we can wish for are approximations. So they are good solutions, but not necessarily the optimal solution. So very often testing all combinations exhaustively is just prohibitively expensive. We can't do this. A little bit, maybe if we don't mind to go for a slightly weaker goal instead of testing all combinations. Maybe we are happy with just testing pairs of interactions. And it turns out that we can do this, and it is often sufficient to already test for pairs. And the test suites will be a lot smaller. When we go for pairs, then this is often called pairwise testing, and this is actually one of the most widely studied combinatorial interaction testing problems, pairwise testing. And in a pairwise test suite covers all 2-way interactions between 2 parameters. There are also 3-way interactions, 4-way interactions. So for 3-way interactions, you have got all triplets, 4-way interactions, all 4 tuples, and so on. So let's look again at our test suite with the 8 cases. So Spain to Barcelona. So these were all the 8 that we had up there about 5 minutes ago. Nothing has happened. Let's see. Are we covering all pairs? I hope we do. So Spain and Barcelona is covered. Spain and Madrid is covered. That's easy. Spain and 20th of August, 21st of August. Spain and 27th, 26th of August. So that's all covered. How about now the cities? So Barcelona 20, Barcelona 21st, Madrid 20th, Madrid 21st. Barcelona 27th, 26th, Madrid 26th, 27th. These combinations 20, 27, 21. So we're covering off always pairs. Right? If we would go for triplets, we would have to do, for example, Spain, Barcelona 20th, Spain, Barcelona 21st. Okay, good. So that's covered. Good. So these are all pairs. It turns out, so this test suite has 8 test cases in total. It turns out that from these 8 you can drop 2 to get a two-way interaction test suite that just consists of 8. Sorry, 6 test cases. Super brief check. Let's just ignore about Spain. So Barcelona 20, Barcelona 21st, what else? Madrid 21st, Madrid 20th. Or do you see a particular combination that is missing?
2 of those for Madrid.
2 and what? 2 and 27 is there?
Madrid for 20th and returning on 26th.
But that's already 3-way interaction. So in the 2-way interaction, so that's what we are interested in right now. In 2-way interaction, it's sufficient to have just pairs. So what you're after is the 3-way, and that comes next, just in about 10 seconds. So I think this actually covers all 6 right now. A bit more general. So we talked about 2-way interactions. A bit more general, we can talk about T-way interactions that covers all interactions of T parameters. For example, 2 or 3 or more. And it's called T-way testing. Yep. And okay, this is nowadays the connection to the covering array or these orthogonal arrays from a few minutes ago. There's just a couple of technical terms. Now, a bit more abstract. I'll guide you through this definition. So in general, a covering array, so let's briefly go back. So a test suite that covers all the T-way interactions, it's called a covering array. Oops, wrong direction. So a covering array with parameters TKV. With this TKV, you can find them on this particular website as well, where people collect these, of a particular size n. So you might remember we had 8 test cases, so that would be a size n, 8, n equals 8. So that's a table with n rows, n test cases, and k columns. Here's the k again. So that's the number of parameters. Each field in this covering array contains a value in the range from, well, these are the different values. So let's say 365 days. So each field in the column has a value somewhere between 0 and 365 or 64. These are small details. And in particular, covering array has the following property. So every combination, or T-way combination, occurs in at least one row. So you might have, for example, I'll go back briefly, the combination Barcelona and 21 and first Barcelona 21st 2 times. This is perfectly fine for a 2-way interaction test suite. Having it several times in there is not a problem. You must have it at least once. Otherwise, it doesn't cover all 2-way interactions. Good. And T, so that's the, for example, 2-way, 3-way. That's called the strength of an array. I'll go back. This was, for example, a 2-way array. So this has strength 2. It covers all 2-way interactions. A little stronger would be a 3-way interaction, or it would be a table with strength 3. And even more powerful or strong, even stronger would be a table with strength 4. Well, 5 doesn't work here because we don't have 5 parameters. And in particular, there is no difference here between 3 and 4 because the one parameter essentially just has one value. So that's the definition. And in general, the optimization problem that we have is now the following. We are after a table of also covering array that covers that has a strength of T, and that's minimal. Why is minimal good? What's the motivation?
To reduce the number of test cases.
Mm-hmm. And as a consequence, this reduces maybe runtime of the test cases. So we don't want to run 2 million test cases. Every time we commit something, we want to run 100 test cases or so. So that's super important. Yeah, we've had that covering array of particular size n. It's like 8. This one is, yes. So that's for v many values, k parameters, t is the strength. Yeah, that's all. And there are lots of these tables online, for example here. Yeah. So this is again our, well, the list or the a minimal table of that has strength 2. The question now is, does that happen to cover all three-way interactions as well? So not just pairs, but threes. And you've already identified it, yes. So, for example, what was missing? Madrid?
Madrid with 20th and the diagonal 26th.
Yes. What can we do about this? How can we fix this table? How can we cover that feature as well? Well, maybe fixing. Fixing is the wrong term. So there are at least 2 combinations that are missing. So if something's missing, we can just create new test cases. We can just add them, the 2 that are missing. That's one way. If we use the 2-way interaction test suite as a starting point and then move over to the 3-way interaction, 3-way testing. Where does this have applications? So we had this motivating example of a web form, some online service where we book some holiday maybe. For web browsers in general, say we can maybe load certain content, be notified or not notified about a blocked pop-up, have cookies, warn about some add-on installations, remember downloads, and there are lots and lots of more behaviors of the system. And we have to test combinations. We'll see soon. Automotive industry, you have one example there in your first assignment, and that first assignment is due end of next week, if I remember correctly. So this is one. For example, you have some driver control, you have some collision avoidance, and you want to parallel parking and so on. Some combinations might not seem very related at first. In this case, we can consider certain constraints. So, for example, some combinations might be, oh no, maybe that's the following way to approach it. The fact that the developer says this will never happen it's maybe not sufficient to say we won't test it, because the developer might make some assumptions. Now, certain combinations don't work. For example, thinking that London is in Spain. So this country-city combination does not make any sense. It's a hard constraint. It doesn't work. But in some other cases, it's probably not a good idea to just make false assumptions or attempt to make assumptions to say that certain situations don't occur. Cell phone industry, we'll use that example later on very briefly as well. So essentially, whenever you have combinations of components or parameters or something where you can make a decision, you can use this idea of testing the interaction between them. And there are many, many more other configurable systems out there. Regarding fault detection, the question now is, or one of the questions that you might ask yourself is, will a pairwise test suite discover any tests that are the result of 3 or more parameters? Well, it might, but it's not a guarantee. There are lots of studies out there that try to, because there's no theory, you cannot characterize a real software engineering product sufficiently so that you can analyze it theoretically. So you can't make statement. You can't prove that certain conditions hold. You can just you can have the system. A particular system that was deployed. You can have your combinatorial interaction test suite. You can run all the tests and then you can then record how many bugs have been found, have been discovered by a particular test suite of strengths 2, 3, 4, 5, 6. And in particular, many studies have found out that once you have 6-way interaction testing, so you consider all combinations of all different of 6 parameters at all times, that covers pretty much 100% of all the bugs. I think there's a figure now. Yes. So this is taken from one older study. for 6 software products. When you look at parameters in isolation, well, let's say on average, maybe you cover or you discover 40% of the bugs. Once you look at pairs, you find about 70-80% of the bugs. So they, or the other way around, based on my estimates now, about 30% of the bugs are the result of an interaction of 2 values. And you can go even further. 3 values, you cover maybe another 10%, 4 parameters, another 5 or 10%. So pairwise testing is a very good start. But in order to cover more, you have to go for 3, 4, and 5-way interaction testing. So we've kind of, I hope we've established that we can create lots of test cases. We can assess their strength in using the term T-way testing, and check, do they cover all pairs of parameters, values, all triplets, and so on. Now, if you have a particular combination, so given is the following: you've got your software system, you've got, in this case, your 8 test cases. Yes, in principle, you are testing all different combinations, but maybe the way the tests are ordered, a certain combination will be tested very late in your, even just a pairwise combination will be tested very late once you run them, when you run them sequentially. So for example, in this particular order, if we have a particular bug relating Spain and Madrid, we would have to run the first 4 test cases. Now in 4 versus 8 test cases, or it's not, you're not going to save very much time with your system, but if you've got 1 million test cases and a particular combination is for the first time tested at step 500 or 500,000, it is going to take a significant amount of time. So yeah, for example, Spain and Madrid. Let's see, we can briefly go through our 8 test cases and check how many new combinations are tested once we go from one test to the next one to the next one. How many more pairs? So for example, here, once we run the first test case, so Spain, Barcelona, 20th of August and 27th of August, this covers 6 pairs, right? So 1, 2, 3, 4, 5, 6. 6 pairs are covered. So this gives us 6 new pairs. If we start with no pairs covered, so no test case run, we go to 6. Okay, these are 1, 2, 3, 4, 5, and 6. Good. Now we do this for the next one. Spain, Barcelona, well, we've covered this before. Okay, no new pairs. But Spain and 21st, this gives us 1 new pair. Spain and 26, we haven't had that before. It gives us another new pair. Barcelona, this gives another one. 3, Barcelona and 26 is another one. And 21st and 26 are another one. All right, and we can do this for the rest. Turns out that for the next one we will cover actually not that much new, and then in the end nothing new is covered. Now maybe we can reorder them a little bit, right? So as we noticed, so Spain and Madrid, that happens relatively late. Maybe we can do something about the order to cover a particular, or potentially cover Spain and Madrid early on this combination. And it turns out that there are ways to create this, and we'll cover an algorithm for this most likely after a break that we'll have in maybe 10 or 15 minutes. So this particular algorithm will create a test suite and also prioritize the combinations. So it will try to have new combinations, as many new combinations as possible early on. Meaning that instead of having this kind of dip here in here, so kind of not really wasting time because you're still covering 1 pair, but you're not using it to the fullest potential. With a reorder test case, you have a fairly high speed, so 6, 6, 2, 2, 1, 1. It doesn't guarantee it. So for example, if you have a problem with, well, we are still covering something new here. 20, what is it, 20, what's the new combination here? It seems to be Barcelona on 27th of August. If for some reason the system has a problem with this particular combination, it will still take 6 steps. There's no guarantee. We can just try to limit such delays to the extent possible. So now previously Spain Madrid was our motivating example was shattered in line 5 or test case 5, and now it happens in test case 2. Well, it's a toy example, but it still serves to show that not only is it important to have the combinations, but also the sequence is important. Well, the sequence is important if you want to get there quickly. I think there should be, yes, lots of research papers on this out there, and I think there will be some plots now, yes. What do these plots show? On the y-axis, on the z-axis, y-axis here, you've got the coverage. So as you slowly process more and more and more of your test suite, so in this case 324, that's simply the size of the test suite for SED, which is a Linux utility. As you execute these 324 test cases, you cover more and more interactions. Of course, once you execute all 324, you cover 100%. Well, that's nothing new, because that's definitely a yes, 5-way interaction test suite. No, and this would be unordered right now. All 324 are unordered, no particular sequence. Once we order them based on the 2-way interactions, so to have kind of like previously to cover as many pairs as possible, so many pairs, and then the number of pairs that are newly covered declines, you can see that the speed at which we cover or we get to 100% is a lot faster. Oops, sorry. So we're here at about 20 tests compared to, well, maybe 60 or 80. So we got a lot faster, and we cover all 2-way interactions. And we can go even one further, slightly further. So you go to investigate the new combinations of 5 parameters. We would be a little bit faster, but you see there's not, so the area under the curve, so that shows how much we cover given the number of test cases we execute. It grows a little bit, but not super quickly. Not that much anymore. So 2-way greatly helps already to speed it up as a consequence, as a side effect. There is no theoretical proof for it, but at least empirically, so in experiments, 2-way helps to make the test case the test suite a lot faster. Well, the test case, it doesn't make the test suite faster. It just helps to detect bugs, which is the one here on the y-axis again, a lot more quickly. So 2-way sequencing is already very helpful. Good. And so again, there is no theoretical proof for it, to the best of my knowledge. But in principle, once you prioritize for pairs, this is not worse than higher strength prioritization. So you could look into 3-way prioritization. So given a particular test case, which one should you next have in your test suite so that you maximize all 3-way, the number of triplets that are uncovered, and then again triplets and again triplets. It turns out going for 2 is already a very good start, and it's very fast to implement as well. Yeah, that's all empirically. So to briefly summarize this first part of the lecture, what have we covered so far? Well, combinatorial interaction testing is a black box technique. Just values go in, and some behavior is then observed. In particular, what's important for us now is that we are after T-way interactions, for example, pairwise interactions. In the last example, was 5-way interactions of parameters. And this is important because many bugs are not the result of just a single input, but of interactions of inputs. We have seen this very briefly when we go from, so in that one case study, from one-way interaction, essentially one value, one parameter-based bugs to 2 and 3, it went from 40% to 70% to 80% detection rate. The 2-way interaction is the most widely studied combinatorial interaction testing technique, and at least empirically, you can use 2-way or pairwise interaction or prioritization in order to speed up the rate at which you discover bugs in your system. Given still the same, for example, it was 324 test cases in that one set example, or previously we had the eight test cases for the web form. Oops, okay. So that should be it for the first part. You can take a short 5-minute break just to let that all sink in. If you have a question, you can ask it. Yeah, we'll continue then in 5 minutes. Yeah, so it's 4 p.m. now. Let's continue in 4 or 5. Let's get back to that. All right. So with this all in mind, what we haven't seen yet is an algorithm that actually that helps you to create a test suite. We've done this manually, and then we've checked a few things manually, but we don't want to do this for 100 parameters, 100 values. That's not great. So what are the options? Well, among other, we could use what's called a greedy algorithm or heuristic. So heuristic are these general purpose approaches, like maybe a random search or so. Alternatively, we can use a greedy approach. And in particular, so what does greedy mean? Greedy tries, so it's again a general concept, and greedy tries to build up a solution by having the most, from one step to the next one to the next step, to have the most improvement at every single step. What this means here, for example, it could mean here that we go from, as we build up our test suite, test case by test case by test case, that we add the tests that increase the number of pairs, for example. The highest number of pairs, highest number of pairs, highest number of pairs. And then gradually it has to tail off a little bit and has to become smaller and smaller and smaller. So there are, for many different combinatorial problems, there are greedy approaches. They are not guaranteed to be optimal, but they can be formulated. Some domain knowledge goes into them, and I'll show you one of these now. The situation is as follows. We have 3 parameters. That's a little bit more abstract now. 2 with 0, with 2 values, 0, 1, 0, 1, and the last one with 3 values. Very simple. It could be, let's say, target city, departure date, and 3 return dates. Think of it this way if you want to. And now our objective is to find a pairwise interaction test suite. So 0, 0, 0, 1, 1, 0, 1, 1, and then all the other pairs here as well. One algorithm published in 2007 is called in-parameter order general. It's just a name that the researchers came up with. And we'll see soon why it's called parameter order. So in general means that there are some other versions, but for us it's sufficient to go with the general version, so IPOG. What does this algorithm do? You can already imagine it's going to be a fairly long algorithm, but once we go through it, it's actually not that complicated. It makes sense once we go through it. So what happens? In the first step, there's a general initialization phase. So our test set is called TS, for test set. So there was our 8 cases a few minutes ago. Right now it's empty because we haven't started yet. Then we have the parameters. So we have 3 parameters. We just say they're in a parameter set, so PS in some order. So it could be P1, P2, P3, or there could be P3, P1, P2, or any order. In our case, we just use P1, P2, P3 as on this slide. So P1, P2, P3. Actually, let me very briefly write this down on the whiteboard. So P1 is value 0 and 1, P2, just so that we can easily remember this, P3, 0, 1, 2. I hope you can kind of see this. It's a very weak pen. Yeah, the window is clear. 2 parameters, and the last one has 2 values, and then the last one has 3. Yes, yeah, the glare is not great. No, it doesn't have curtains at the back. Maybe I can. Maybe on the side. Okay, and this one's not dying on me. Okay, good. Don't worry, we'll see it often enough. Good. So, no test case, 3 parameters in PS parameter set, and now we add to our empty set a test case for each combination of values of the first T parameters, we after pairwise testing, so t is 2. So the third step is add to the test suite, or test set, a test for each combination of the values of the first two parameters, t equals 2. What do we have? Well, we've got two parameters, p1 and p2, and each has two values. So we add two ts, two ts. This is our test suite now. In combinations 0, 0, 0, 1, 1, 0, and 1, 1. Very simple. Next step, and this is going to be a loop. So for integers going from, so t is 2, so t plus 1 is 3, so integer 3 going from 3 less than n, and incrementing it. So now let pi be the set of, also these are not the actual two-way combinations. I'm too close to it, so I can't read this off anymore. So. Involving the parameter pi, so we had the third parameter already, since t is 2. Where do you have it? So t is 2, 2 plus 1 is 3. So we look at parameter 3, and the t minus 1 parameters among the first I minus 1 parameters. So t minus 1 parameters, t is 2, so t minus 1, 2 minus 1 is 1. So we look at parameter 3, and the one parameter among the first, I is 3, among the first two parameters. What does this mean? So for the third parameter, and every individual here, we add a combination. That's all that it means. So we had, I'll go back once. So for parameter 3, and we've got one parameter for all one parameter combination in the first two parameters. So the third parameter for each single one of the first two. So we've got P3 with our three values. Did we have this here for the three values? The set of t-way combinations. Yes, because it's the values involving parameter 3. So values 0, 1, 2, and all the different combinations here. So one value combination, 0, 0 and 0, 0 and 1, of all the all of the previous ones individually. And this gives us our set of combinations pi. Now based on this so these are not our test cases yet. They're incomplete. They're having some undefined fields here. This for now is just our set of combinations pi. How do we create test cases out of these now? This is where the next loop comes helpful. So for each test, now in our test case, we choose a value for that third parameter. Remember, we are already at 3, so 2 plus 1 is 3. So we look at 3. So choose a value vi for that third parameter and replace the combination that we have so that where we insert this one value vi. So that the newly created gamma prime covers the most number of combinations in pi. So pi was this list of 8 or 16. So this is all pi. So it covers as many of these combinations as possible. And then we'll remove from pi what we are covering. We'll see this. So this was previously our test suite from, go back. Oops, sorry. So all combinations of the first two parameters, but we're just at two parameters, right? And this is now a two-way interaction test suite for two parameters, but we're missing the third one. How do we add the third one? Well, this one was this intermediate step where we consider, we need to have all the combinations of all the pairwise combinations with whatever happens with the first two parameters. That's what happened in the previous loop. Now what happens here is the following. Well, we add to the test case, so we make the test case longer than from the previous one, right? So previously we had 0, 0. Now we add one of the values from from pi, one combination, and in particular we add that combination that ends up covering the most. We add that test. We extend this test case in such a way that the new test case covers as many combinations in pi as possible. This is how we prioritize the test suite. Now, if we have, because this one is our first test case right now, 0, 0, we can go through this one. So we've got, where do we have 0, zeros? Where do we cover P1 equals 0 and P2 equals 0? Definitely cover it here. So 0, undefined 0 here. This one could be just as well. We could pick this as well. So there's 0, 0 combination here. It's covered, or would cover two combinations. But similarly here, 0, 0, 1 could just work just as well. 0, 0, 2 could work just as well. In all cases, so two combinations are covered, two combinations are covered, two combinations are covered. And it wouldn't matter. So this could be 0, 0, 0, 0, 0, 1, 0, 0, 2. It's always two that are covered. Then we go to the next test case of our original ones. So we had 0, 1 previously. All right, 0, 1. Well, 0, 1 doesn't work anymore because this one's already eliminated. We are covering this already, right? So we're ignoring this. Whatever is orange, let's ignore this. So 0, 1, where do we have this? 0, 1 could work. What else? 0, 1 could work. 0, 1 could work. Okay, well 0, 1 could work here as well. So 1 at the end or 2 at the end. In both cases, 2 are covered. The slides simply proceed here with the 1. The 2 could be picked here just as well. It doesn't matter. No, doesn't matter at all. Next go. So again, third test case, right? 1, 0 was the old previous combination. We look for in the old combination. So I have to go back. Yeah. So now that we are at this step, we need to populate this with some value from P3 so that we cover as many combinations here as possible. That's again the greedy step. What do we still have? Well, 1, 0, 2, 1, 0, 0 could be 1, 0, 1, 1, 0, 2. Again, we've got lots of options. The slides proceed with, what is it? 1, 0, 1. Could have been 1, 0, 2 here as well, just as well. Two combinations are covered. Then we have one last one. 1, 1, and then some value is missing right now. Well, what could we do? We have 1, 1, wait, sorry, yep. 1, 1, we could do 1, 1, 0 or 1, 1, 2. The slides proceed with 1, 1, 0, that's all. And now we have an interesting situation. We still have some combinations not covered. See, 0, x, 2, we don't have that yet. So we've added to our original 4 test cases. We've extended them by this third parameter. We've gone through our list. We've added them. We've added that value here for the third parameter that makes that covers the most combinations here from all the combinations. And we are left with a couple of combinations that we are not covering yet. So we need a bit more code, a bit more pseudocode. So we removed all the combinations, so this all turned orange here in step 8. And now for all the combinations that are still left in that set pi, there were 4 combinations in there. If there is a test that already covers it, then remove it. Otherwise, change an existing test case or add a new one. I know that, well, this one is a bit vague, so let's just go with create a new test case. So this is our current situation. Well, for example, 2, 2, 0 is missing, so 2, 2, 0, 0, so with 0, 0, 2, 0, 0, 2, 1, 1, 2. These 2 could be added. Or we could add 0, 1, 2, because this would cover 0, 1, 2, this one, and 0, 1, 2, also this one. So there are at least 2 different combinations of 2 additional test cases that could be added. So 0, 0, 2, or 0, 1, 2, or 1, 2, 1, 1, 0, 2. And now everything's removed from our combinations. And that's it. I'll go back briefly. And that's the entire algorithm. And now it looks, well, at first sight, very complicated, but it's actually not that bad. It's really not that bad. What it does is, again, it starts with an empty set. It first, okay, well, then you have the order of the test, of the parameters in some order. Then you add all, for example, 2y combinations of the first two parameters, and then you start adding more columns. You add one column, one parameter, you add another parameter, and whenever you add another parameter, that's then this loop here, so for int, and this goes up to the number of parameters that you have, here up to n. So if you have 20 parameters, you would add parameter 3, parameter 4, parameter 5, parameter 6, parameter 7, and so on, one by one by one. And for each addition, you would do a new pi table. So all the combinations of all the values that you have, your, let's say, 6 parameter, 6 with all the previous individual ones. So this pi gets fairly large, and then you check again, okay, are you already covering it? Are you covering it? Or actually, it's the other way around, sorry, you're not checking, are you already covering it? I should not have said that. What you're doing is you're picking the value so that once you add this, so the VI is new, once you add this for your, let's say, 6 parameter, some value, so that the amount of orange here in pi is the most that you add. This way you prioritize it. Up. Yeah, that's our outcome. Six tests. And this is what the algorithm does. So it's it adds the largest number of T-way interactions at every in each iteration. Very problem specific, but it's also guaranteed to produce a solution. Sorry, back here. So it will create a test suite. You will still have to go through all the through all the parameters up to n, obviously, because otherwise you're not covering all n. You do this over and over and over again, and it will produce a test suite. Not necessarily a minimal one, but an attempt to prioritize whenever you add a parameter. And this, unfortunately, also means that depending on how your parameters are ordered, so in this case we had parameter 1, parameter 2, parameter 3, if you would do it in a different order, let's say parameter 3 first with the 3 values, and then 2, and then parameter 1, your test suite might look different. And also it might be longer or smaller, or larger and smaller. So that's a test suite. And it prioritizes this. And this is nice, a nice feature of this IPOG. In parameter order general, ignore that word for now, but in parameter order. Builds it up. There's an exercise here that I'll just skip for now. So this is something for you to follow through later if you want to at home. And there's a solution also there as well, but you can follow, and that's maybe a nice thing to do before attempting assignment 1. Go through this exercise to see whether you've understood it properly, and then continue with the assignment. There's a lot more information, voluntary information, and more tests. What I want to jump to now is this example. We could use the very same algorithm, so IPOG, to work on this particular, work on this scenario. And it can give us this particular table. It doesn't matter, we're just skipping all the intermediate steps, because we've seen this once and we could apply them again. So this one here has, I think it was 18 test cases now. 2, 4, 6, 8, 10, 12, 14, 16, yeah, 18 test cases. Oh, wait a second, actually. Well, I did a mistake. It's not a full test suite. So, sorry about that. First parameter, 3 options. Second parameter, 2 options. Cookies has three options again, or 3 values. So 3 times 2 times 3. This gives us, without even considering the one before add-ons install, these 18 combinations. These are all. There is not a particular minimized test suite whatsoever. It's just brute force enumerated, all 18. No smartness whatsoever. So yeah, 3 choices, 2 choices, 3 choices. We can, and this gives us the 18 interactions. We can do the same, because we are, right now, I should have said that, because we are not after 2-way interactions, but 3-way interactions. Right? We've seen briefly that in empirical analyses on studies, 3-way interactions, they can detect more bugs than 2-way interactions. So that's why we are, in this particular case, after 3-way interactions. So first we had the first 3 parameters. If we are now considering all the 3-way interactions of the first parameter with the second parameter and the fourth parameter, or 3 times 2 times 2 combinations, gives us 12 interactions again. The last 3, 2 times 3 times 2 is again 12. Did we forget one? Oh yes, we forgot one. So there was first one was third and fourth. So another 18 interactions, or 18 interactions in total. So in principle, we might think that there are 18 interactions and then 12, so for all the different triplets, right? So 18 plus 12 plus 12 plus 18, so that's 60. That is 60. We can definitely do a lot better. We don't need to have all 60 test cases, luckily. For example, we can use IPOG to create a test suite that is a lot smaller.
Can we take all these 4 together, like 3 into 2 into 3 into 2? Make it a 4-way.
That is possible, yes. So
that will give us different, like 3 into 2, 6 into 3, 18 into 2 is 36.
36. So 3 times 2. Yes, 1 second. Yes. So it gives us 30 seconds. Yes, correct. Because we are already covering a lot of these combinations. So the overall the statement here is misleading because it covers a lot of the other. It's misleading and a little bit on purpose. Just for example, to point you at what you've just said. So you can, a 4-way interaction suite should not be smaller than a 3-way interaction suite. If you wouldn't think about it too much and just try to decompose the problem. So we've got 4 parameters, and we now look at all 3 out of 4 combinations and deal with them completely independently. Then we would need 60 combinations in total. But among these 60, there are lots of them that already cover certain 3-way interactions. If we're after 4-way interactions, yes, then it's 3 times 2 times 3 times 2. So the 36, yes. Which means that the 60, there are definitely duplicates in there. Because 36 would already be the brute force table. 60 is then just, we've got lots of duplicates in there. Yeah, good point, well observed, definitely. So what's a lower bound? What's probably a good number for the smallest test suite that we can create? Because it's a minimization problem after all. We know that 60 is too large, because we can apparently at least do it with 36, right? What's probably the smallest number, a smallest number that we can say we need? Yes, we definitely need at least this many test cases. Okay, let me see. Maybe I can rephrase this a little differently. Yeah. So 36 is definitely enough. So 60 is more than enough. 36 is definitely enough. What's the? Maybe let's think about it the other way around. How many do we at least need to cover all 3-way interactions?
3-way, at least 60.
At least 60. Well, you have already observed that with 36 you're covering all combinations. So 36 would be even 36 would be more than should be sufficient, because 36 is.
We are taking 4.
But in the correct, when you take all 4. But if you're considering all 4-way interactions, you're already enumerating all different combinations of the 4. So this already includes all the 3-way interactions as well. Let me turn it around. Is 1 test case enough? No, unlikely. Huh? 2? 2 test cases. No, I'll try the following. Are 12 test cases enough? Can they be enough? Maybe. How about the 18? What do you think is the difference between the 18 and the 12?
6 more cases.
Okay, it's 6 more. Yes, yeah, good.
Better probability.
If you do only 12, how can you cover all 18 here? So you definitely need at least the largest number that you have here in your decomposed problem. Where is it here? You definitely need at least the 18, because otherwise you're missing out on some combinations of 3 parameters. I know that was maybe a little bit a trick question. But it is, well, we do not know until we solve it whether 18 is actually correct. So 18 theoretically has the, we know that we need at least 18, because 17 misses out on one of these. We do not know whether 18 is perfect. 19 might be, maybe 20, maybe 21. So we have to solve the problem first. We have to prove that it's maybe 18. It's just a different way of thinking about the problem, because you might think, it's 60 is a really large number, 36 is still a really relatively large number, but somewhere between, or including 18, is the truth. So it turns out that you can create a test suite of 18 test cases to cover all 3-way interactions. And where we can go through them all in, it's not really necessary, I think. And that actually, it's based on essentially the first 3. So we need to cover at least these 18 interactions. They checked. All right. And now we do something interesting. Let's say we have these test cases, and the customer comes along and says, when we restrict the loading of some content, then we only have the outcome that we need to have some notification about blocked pop-ups. That's the only combination that so we need to have this particular combination in there. Other combinations of restrict and notify, or the other way around, load content restrict and notify pop-up blocked no is infeasible. It's not supposed to work anyway. So it's a clear no from the customer. Where do we see this in our test case? In our 18 test cases. So restrict in this column here and notify pop-up blocked yes. So restrict yes here, for example. Restrict yes. So 2 test cases violate what the customer has specified. Sorry, the other way around. I confused myself. So how did I do this? Correct. We're just considering this particular combination. So we are kicking out. We see that in 3 cases the tests are violating what the customer wants. So this way around, yes. Yeah. So when it's restricted, the loading of content, then the pop-ups we have to be notified about them. Since the 3 test cases are violating what the customer wants, well, what can we do? If it's not allowed, if it's a violation, we could just remove the test cases. If the test case is not supposed to succeed, we can drop them. So out of 18 test cases, now we are down to 15. There is a bit of a problem now with the 15 test cases. Are we still covering all the 3-way interactions of the previous that we previously had covered? So the 18 previously was covering all 3-way interactions. We've dropped 3 test cases, and it turns out that certain combinations are missing. So load content restrict, cookies allow, and yes is missing. Restrict, allow, yes is not there. Correct. So this particular this particular 3-way interaction is no longer there. Oops. So we've removed the 3 test cases. In the remaining 15, this particular combination at the top is missing. It didn't have anything to do with what was it here? Restrict and notify pop-up locked, yes. But this particular combination is now missing. So what do we do? We could say, okay, so this previous combination, so whenever we have restrict, so what was it here? So restrict cookies allow yes, and one before I add-ons install yes. We could just take 3 test cases or take some test cases, and whenever it's also going back to the original 18, we could tick the 3 that are violating, that we would otherwise kick out, and make them go from no, which is violating the condition, to a yes. Now in this case as well, some combinations are not covered anymore. So instead of going from 18 to 15, we went from 18 to, again, 18, updated our test cases so that we don't violate the condition anymore. But now we are again missing out on certain combinations. So notify pop-up no. Do we have that somewhere? No cookies allow yes, so no allow and yes, no allow and yes. I'm not seeing it. No, no allow, no, no allow, no. So some combination. So we've super briefly seen 2 maybe naive ways of trying to fix the problem. Again, starting situation was the following. We have one constraint. So we don't want to test, so this is a harder constraint. When it's restricted, then we have to test this feature. 3 test cases were violating it. We could drop the 3 that are violating it, or we can try to fix them. But dropping led to some combination being missing. And fixing them in the sense that we should never have restrict no, but always have restrict yes. Fixing them still resulted in some 3-way interactions missing, because we have 4 parameters. So what can we do? Well, let's go back to dropping test cases. So we have the 18, we have the 3 test cases of the 18 that are violating what we should be testing. So what are the 3-way interactions that are, assuming that we take them out, which ones are the ones that are missing? In particular, these are the ones. So we have, I'll go back briefly, so we have restrict no, allow yes. So what's being dropped then? Restrict no, allow yes, drops the following 2 3-way interactions. So allow yes stays with restrict, and allow yes and no. Similarly for the next, where was it here? 7, restrict no, restrict no, restrict no, restrict no. We have, once we drop this, we would miss out on 2 3-way interactions. Restrict no stays in both cases, and once restrict, once no. These are the 2 3-way interactions that we would drop. And the same again for 17. So we drop 3 cases, the red ones, but we would at the same time lose out on 6 of the 3-way interactions, which is not good. So these are the 6 that we are missing out, that we are losing, once we drop 3 of the tests. Okay, so let's go back to, once we have dropped these 3, we can check. So is it load content, so restrict, allow, and yes. Restrict, allow, and yes. Is this covered by the remaining 15? It's not in there. Restrict, allow, and yes. I just see a restrict, allow, no. So the purpose, sorry, I should have said that. Now that we have these 6 that are missing, we can just, we can check against our remaining list of 15 test cases. Maybe they are still covered by something. So the fact that out of each test case, we can create these 2-way interactions just by looking at each test case individually. We don't have to look at the remaining test suite at all. But now we can go through the 6 3-way interactions and check, are we maybe still covering them anyway? And this is what happens here. So this is the first 3-way interaction that we can't find in this table. The second one is missing. I think the third one is, no, the fourth one is there. So the fourth one is there. So the 4th combination is no, restrict, and no. Let me just briefly go back. 4th one here, no, restrict, no. So even though we lose this, no, where's no, no, restrict, no. So that's not too bad. We can drop this, well, when we dropped that test case number 7, we are not missing out on this particular three-way interaction. We do this for the 5th and the 6th as well. And in summary of these 6 three-way interactions, our 15 test cases are still covering 2. Now we still have the problem of the remaining 4. 4 three-way interactions are still to be covered. They are still missing. What can we do? We've got 15 test cases. These 4 are missing. Maybe changing test cases again is maybe not an option, because then we have to check lots of test cases again. If a combination is missing, maybe we just add new test cases again. So one way is to simply add the 4 three-way interactions as new test cases. So we had initially we had 18. That's because that's why the numbers go up to 18 here. We dropped 3. And after checking which ones are still covered, which three-way interactions are still covered, we have these 4 left over. And now we just have to fill the gaps in here. We can, for example, we can set the first one to yes. So that's important, because no was not an option anyway. So we have to set restrict and yes, this particular combination. That was the constraint given. And then we can, for block, for the first one, we could use block, or restrict is not an option, because then we would violate the constraint again. So restrict and no is never an option. So block is an option, or allow and no would be an option as well. So in the end, instead of having 18 test cases, instead of having 15 after deleting some, or having 18 by changing some values, but then missing out on some three-way interactions, what we've done now was go from 18 to 15, analyze what we're missing, and then we added 4 again, which gives us 15 plus 4, 19 test cases. Long story short, or no, I think one of the interesting pieces here is the following. The customer said we should not test for a particular combination, and as a consequence, the test suite got larger. I think that's an interesting observation here. So maybe a bit counterintuitive. Normally I would think when you add constraints to the system, when you're not allowing certain combinations, maybe you have to test less. But here it turns out, because we had a very compact test suite in the beginning, which was essentially very, very efficient at checking the three-way interactions. Once we dropped particular combinations from there, it was not that efficient anymore, and now we are left with 19 instead of 18 test cases. So that's maybe the counterintuitive aspect. I think that constraints can be used to reduce the test suite, but it's not the case. Now, this one was a particular example. In the real world, test constraints might actually help you to reduce your test suite. What wasn't the case here in this particular example. Good. Let me jump to, one more aspect that I want to briefly cover. And that's the following. Now, this one here. You might think, okay, that was all again very abstract with different parameters, and we've just talked about four parameters and a web browser, a web application. Modern user interfaces have a lot more parameters, a lot more options. So in this case, there are about six or seven booleans. So we can turn this on and off, this parameter we can turn on and off, this one on and off, this one on and off. Here we have 2 choices, here we've got 3 choices, here we've got a couple of choices maybe. So if you want to do all 2-way, 3-way, 4-way, you can imagine that's actually a very large number. So we've got 2 there, for example. We've got a search, colors, 4, oops, that was too far. 4 for the browser, 6 options here again, or 7, and so on. So in total, we've got roughly 7 Boolean parameters to test, and some of them have 3 values, and one of them has 5 values, one with 7, I think it was maybe recent items, one with 10 values even, in this case, maybe that was the color. So in total we've got 12 parameters, 42 values. The nice thing now is there are plenty of tools out there that will help you to generate test suites to cover all the, for example, pairwise interactions. And it can be encoded on an abstract level very, very easily. So Casa would, for example, take this string here of 2 parameters. So each parameter here is just given as the number of values. So parameter 1 has 2 values. These are our booleans. 2 parameters, 2 values, 2 values, 10 values, 3 values, 3 values, and so on. And you will have to tell Casa in this case that you're looking after pairwise interactions, or 3-way interactions, or 4-way interactions for the 12 parameters. And in total, your search space would actually be 400,000 test cases. And luckily, Casa can produce something instead of 400,000 test cases. It can produce something in the order of 70 test cases in under a second. So even though this looks maybe like a relatively large search space, and this running all 700,000 test cases for something like this or some user interface would take an awful lot of time. But 70 test cases, first, becomes manageable, and second, the tool itself that generated these 70 takes hardly any time. That's then one of the contributions essentially here from the research side to create test cases, so test suites for your particular application very, very quickly. And it's also based on this encoding here, so two-way interaction. So one line, that's what the tool takes as input, one line with a 2, one just saying, okay, 12 parameters come up, and these are just the different values. Yes, you will, of course, still have to translate. Let's say this tool here is use LCD font smoothing when available, either it's turned on or off. But you don't have to worry about the creation of this table anymore, these 70 test cases. Yep. If you're after a 3-way interaction, so that would use a 3 here instead of a 2, 3-way interaction, then instead of 70 test cases, you end up with 354 test cases, and it takes a little longer, instead of under a second, still 24 seconds. But that's okay, that's still manageable. Just keep in mind that 3-way interactions still doesn't cover potentially, or at least empirically, as many, it doesn't detect as many bugs as 4-way interactions, again, not as many as 5-way interactions. So, summary now of this second part today. And you cover some part of the first hour as well. So, a combinatorial interaction test suite attempts to cover all 2-way interactions between any 2 parameters or T parameters, T-way interactions. Finding a minimal test suite is a very challenging task. And actually minimal, finding a small test suite is a different problem. So finding a small one, we can use IPOG, for example, this very long algorithm that we've seen. The most popular approaches, so what we've seen today was only the greedy approach, so IPOG. You can also use meta-heuristic approaches, like random search. You can create your tables randomly, but you might not have any guarantees in there whatsoever about covering all 2-way interactions. What you can do is, for example, use hill climbing, and then also use some penalty terms. So normally in hill climbing, hill climbing or hill descent, let's say you would minimize the test suite, but you need something that pushes you towards a valid solution in the first place. So valid solution here means that you cover, for example, all 2-way interactions. If you use something like a hill climbing approach now, how can you encourage your algorithm to find a solution, a test suite that covers all pairwise interactions? Well, for example, whenever a particular interaction is missing, you give it a big penalty. For each penalty, it costs you 1,000 units. As in maybe plus, it adds it. So that's maybe a way to think of it very easily. So you have you're not minimizing the number of rows, the number of test cases, but you're minimizing the number of rows number of test cases, plus 1,000 times the number of two-way interactions that are missing. This means that whenever the algorithm manages to cover another two-way interaction, it will drop your test suite quality by 1,000, which is a lot more worth than finding another, than dropping a particular test case. So the idea of this penalty then is to push your algorithm first into finding something that is valid, that covers all two-way interactions, because whenever it covers one, it will drop so much that it will accept it. And then later on, it will fine-tune and try to drop some lines again as well. But that's a little bit beyond what we're covering and also what's being needed for the assignment. In general, greedy approaches they produce test suites that are not minimal. They can be relatively large, or they are larger than what some meta-heuristic search algorithms can find, like maybe a hill climbing with some penalties, with some tweaks. The problem is you've got a little bit of trade-off. You have a greedy approach that had, for example, this relatively long algorithm there that has a very fixed number of loops that it will perform, and then afterwards it is simply done. In a meta-heuristic approach with your hill climbing, maybe you have to perform a restart, maybe you have to run it just longer and longer because you don't know when it's done. When it's really done, it will have created something, but you never have an idea when it's. Can it still make progress? Can it still make progress? So as a consequence, something like hill climbing takes longer, typically, but also finds smaller test suites. That's just something to keep in mind. So greedy approaches are often problem-specific, very quick, but not as good as something that is a bit more general, but then that can then also be better. Yes. So that's a bit the trade-off, speed versus quality. Yep. And okay, that's not entirely true. So constraints can help to reduce the test rate further once you know about constraints. So once you know that certain conditions are simply never true or cannot happen in practice. Maybe in engineering, this could be like, or when dealing with cars, this engine and this particular, rangefinder, they are never an option. No customer can order this, so you don't have to test this particular order. Yeah. Oh yes, and thanks to tools that we have, many free tools are available to do this. Two-way testing for three-way testing, four-way testing, and so on, they actually become feasible, and you don't end up with an awful lot of number of test cases. So with five-way testing and a couple of parameters, you end up with test suites of hundreds and hundreds or thousands of test cases. But once you consider the constraints, it will actually reduce the test suite. In our case here that we had with the web browser and the 18 test cases that ended up being 19, that was a particular example to show this doesn't always hold, that your test suite gets smaller, but it can actually get smaller. Because when you have many parameters, you're very likely to cover certain combinations anyway. Once you consider constraints. So when you consider constraints, it will remove some of the test cases, but then because you have many test cases anyway, you're considering many combinations, it's very likely that some of these other test cases are covering the combinations that you've just removed. Yep. All right. On the slides, I have covered a couple of sections. The sections that I've covered are for your the sections that I've skipped today. They are for your information if you want to learn more about the domain. They are not relevant to the assignment. There are, however, in there some additional exercises like this one here, for example, but there's not the solution in here. There are some other exercises in there as well. So that's something for you to practice for the assignment, for example.
Are these based on any algorithms, the greedy algorithms that we discussed?
Say that once more, please.
Are they based on the greedy algorithms that we just discussed? The practice questions or
Other practice? The ones for some you can use the greedy algorithm, definitely, yes. So for the assignment you don't have to implement anything. You can do this by hand. You can use IPOG. You're not I have to double check the text. No, I'll have to double check before I make any other statement. So you can use what we've covered today to answer the assignment, definitely.
When is the due date of the assignment?
For assignment 1, it should be end of next week.
Next week?
Next week, yes.
Oh.
Yes. Some of the questions are, I think, very simple, and they just encourage you to learn a bit about more the domain.
In the assignment?
In the assignment, yes.
The assignment was the presentation and the essay, right?
No, there are also more aspects. There is, sorry, I'll briefly change to the